We're going to calculate the electric field due to a partially circular charge distribution that looks like this. So it is uniformly charged, and so what we can do is just note that we sweep out an angle theta. We actually go from negative theta to positive theta, and we are integrating around the ring. One thing I want to point out is we can make this little hunk of charge dq equal to q over L times this little hunk of dl that goes across the charge distribution, which is very nice. Now, one thing I want to say about dl itself, though, is we know that when we go around a circle, the circumference of the circle is 2 pi radians times the radius, and any other little hunk of circle L would be given by 2 pi times the angle in radians. So a little hunk of circle dl is going to have the length, length L equals the angle in radians times the radius. So dl, a little hunk of circle like this, would have a length d theta times the radius, where I would take a little sliver d theta and times it by the radius to get that length right there. So with that in mind, we're going to set up our electric field. The other thing we want to note is that there is a symmetry to this problem, so that there's a portion of electric field that the electric field actually points along the radial direction, and it turns out that only the x component matters. So the electric field that we actually care about at the center of the circle is given by the EX, the x component, which is going to be E cosine theta. And so what we're going to integrate is the following: 1 over 4 pi epsilon naught dq over r squared times the cosine of theta, since it's the x component. Keeping that in mind, we have here, I'll write it here, that q over L equals r. Q over L times dl can be written as q over L times r d theta. And so this is the expression we're going to integrate. We're going to integrate 1 over 4 pi epsilon naught. We're integrating over the charge distribution, which is going to be q over L times r d theta times 1 over r squared times the cosine of theta. And we're integrating from negative theta to positive theta. So as we continue here, we're going to get 1 over 4 pi epsilon naught. Let's factor out all that we can. So q over r times L when I do some cancellation. And then we're integrating negative theta to positive theta of cosine of theta. So when we integrate this out, this is going to integrate to 1 over 4 pi epsilon naught q over r L, which is just r times theta, but we'll just simplify that in a second, times the sine of theta integrated from negative theta to theta. So we're going to end up getting 1 over 4 pi epsilon naught q over r L times 2 sine of theta. Now I can write L in terms of the angle that swept out that sum r times 2 theta, if you'd like. So when I integrate this out, I'm going to end up getting, I may sub in that, I may not sub that in there, but I'm just going to write this as 1 over 4 pi epsilon, actually I'm going to simplify this, 1 over 2 pi epsilon naught q over r L times the sine of theta, and that is our answer for the electric field.